f64. As you can see over here, we have x which holds an f64 type. So we can call this method on x, right? Again, this is a method and not a function. So the problem over here is that self in this case would be f32, which is not the right type. So let's change that, f64. And that means self over here would be of type f64, the concrete type we are providing here. And then, of course, the return type would be f64, right? Because we are here performing an operation on two f64 types. Now, over here, of course, we have to provide floating point values, right? Because again, this method is only implemented for a point that holds as fields f64 types, like that. Right. And then we can use this method as defined in the standard library. And of course, over here, we just have to annotate one type, right? Because we only have one generic type parameter. And as you can see, this is compiling, and I will see you next time. So I've told you that we will take a brief look at const generics, and I will just solve one exercise and leave it at that, because const generics is a more advanced topic and you don't need it that much in your everyday programming. So they're useful at some situations, but they are not that much used. So let's see an example over here. We have here a struct array. So we have here the struct array, which defines two generic type parameters, t and n. Now t is a generic type parameter and n over here is a const generic type parameter. And as you can see, each array struct holds a data field with an array of type t and n elements. All right. So when we look over here, we have an array, and I will now annotate this type of type array, right? This struct we have defined over here. We are holding three instances, as you can see, 1, 2, 3, three instances of this array struct, right? Like that. Now, I have told you that when we have generic type parameters, it becomes part of its annotation. So we have to annotate it over here too. In fact, we don't have to do that because it's usually inferred by the compiler, but I will do it right now. So this over here cares about the types in the array the data field holds. So as you can see, we have here integers, we have here floats, and over here we again have integers. And what that means is that in this array over here, these actually should all hold the same type, because we have to provide here a concrete type, right, for t, and that means this data field over here will then hold in its array this type. So in this case, we will do i32, and we need to provide it a constant, meaning for the length of the array. In this case, we define 3, all right? And what that means is that the arrays inside the data field of these instances must be of i32 type, and they must have a length of 3, right? So we can't use floats here, we have to use i32. And over here we need to add another element. Now they can't be different. For example, let's do it like that. That is possible, but all of them over here must have the same type and the same amount of elements, because we are annotating that here, so it complies with the generic type parameter annotations here. Now let's create another array with floats. Now I want this to hold array instances of type F64, and let's do 2 elements. And I will pass here, let's say also 3. And that means inside here, let's first look at the outside array, at this array over here. So we want 3 elements of type array, this array struct, all right? So let's define that. Like that. As you can see, we have here 3 elements of type array. Now we define here for the generic type parameters that the data field should hold an array, right? Because this is defined over here in the array struct. So each data field should hold an array of F64, right? The T over here of 2 elements, right? This is the const generic parameter. So we are passing here a constant and not a type. So in this case, the data field would have concrete types of F64 and 2 elements, right? So let's fill that out. Like that. As you can see, this is compiling because we are here complying with the generic type parameters. We have 3 array instances, right? And each array instance holds a data field with these types, F64, and they have to be 2 elements inside the array. All right, see you in the next topic. We will now cover traits. So a trait is a set of methods that can be implemented for multiple types in order to provide common functionality and behavior between them. A trait consists only of method signatures, which then have to be implemented by the target type. It's similar to classes in other languages, but not quite the same. And it defines shared behavior in an abstract way. So let's see how that might look like. As you can see over here, we have 2 custom types, sheep and cow. Now we want to indicate that these are somewhat related. So over here we have created a trait animal, which defines 1 method. Then over here we are implementing the animal trait for sheep and for cow. Now when we implement a trait for some type, then we have to implement all the methods the trait defines. So in this case, as you can see, in the trait animal, we only provide it with a function signature. And then the concrete types, for example, sheep and cow, will implement the method and its behavior. So as you can see, both sheep and cow then implement the animal trait, meaning they automatically implement the method, right? So both of them take a reference to its instance, for example, a sheep instance, and then just return the string over here. And the same thing for cow. Now there is also derivable traits, and we have seen that before. A trait can be automatically implemented for a struct or an enum by the Rust compiler. These are called derivable because they can be derived automatically. And the most common derivable traits are debug, allowing to output content via this debug notation. We have seen that. Clone, which enables a type to be duplicated with the clone method. Copy enables a type to be copied implicitly without requiring explicit clone method. And partially Q enables comparison. Now we can pass traits as parameters. So the notify function over here takes as an argument any type that implements the summary trait, meaning we can ensure that the item argument over here implements the summarize method, right? If we provide here a type that didn't implement the summary trait, then it wouldn't have this summarize method. Traits can be used as parameters for functions. The function notify takes as an argument any type that has implemented the summary trait. Now there is also a concept called trait bounds, meaning if we declare over here a generic type parameter, we can define that the type over here must implement the summary trait. So the argument we pass to this notify function must implement the summary trait. And this is similar to the example using the impl summary, but more verbose. So as you can see, this would actually be exactly the same like we did over here. Trait bounds are declared like generics after the name of the function, and use trait bounds if you have lots of parameters to avoid this. So if we would have here an argument which takes a type that implements summary and another argument which again takes a type that implements summary, we can do it like that. So we define here a trait bound, meaning the generic type T must implement the summary trait. So both argument 1 and argument 2 take a reference to a type that implements the summary trait. And if you have big trait bounds, like for example this, we have here generic type parameter T, and we say here that the type T has to implement the display and the clone traits. And the generic type U has to implement the clone and the debug trait, right? And then over here, as you can see, the first argument must be of type T and the second one of type U, and we are taking references. So we can write that in a more concise way using a where clause, meaning after the return type in a function, we can use the where keyword and then over here define our trait bounds. And this over here is exactly the same as this. But instead of defining the trait bounds directly on the generic type parameter, we do it in a separate block. And we can also return from a function a type that implements a specific trait. So as you can see, the return dog function over here returns an instance of the dog struct. And because the animal trait over here has been implemented for dog, we can also define the return type as follows. We return here an instance of dog, meaning we return here a type that implements the animal trait, because as you can see, animal is implemented for the dog struct. Let's see exercise 1. Fill in the 2 impl blocks to make the code work. Don't modify the code in main. Now we have here a trait hello, defining 2 methods. Now over here you can see that we didn't only provide the function signature, but we implemented basically the whole method. Why is that? Because this is considered the default implementation, meaning any type that implements the hello trait automatically gets this default implementation of this method. So we don't have then to implement it manually. It will automatically get implemented for the type that implements the hello trait. But as you can see over here, we have a method which is here just a function signature. So we have to implement that manually. Then over here we have 2 structs, student and teacher, and we implement over here the hello trait for student and for teacher. So let's see, we have here an instance of student, and as you can see, this is just a struct that doesn't hold any values, right? So we instantiate it like that. But because we have here implemented hello for the student struct, that means we can then call upon it this method over here. As you can see, we call the say hi method on the S instance, and then it should return hi. Now we don't have to implement the say hi method over here again, like that. We don't have to do that because it's already implemented by default, right? But what we have to implement is the say something method, because as you can see, we are calling the say something method on the instance of S. And remember, when we implement a trait for a type, in this case student, we have to implement all the methods except the default implementation here. So let's actually take this and copy it over, because the function signature must be exactly the same like defined in the trait. And then over here we want the return to be I'm a good student. So let's return this string here. Like that. So when we call on an instance of student this say something method, then it will return I'm a good student. Now over here we are instantiating the teacher struct. And as you can see, we are calling the method on the T instance, and this should be the returned string. So as you can see, this is different from what is implemented in the default implementation. And that means we have to re-implement this say hi method for the teacher type. And the return string should be hi, I'm your new teacher. So as you can see, if a trait defines a default implementation, we can also overwrite the default implementation and provide another return value. And of course, because we have to implement this over here, I will copy that and I will implement it for the teacher type. So as you can see, when we call the say something method on an instance of teacher, then we should get back this string. So as you can see, we have then implemented the hello trait for our custom types, student and teacher. Let's see if that compiles. And this is compiling. Derive. The compiler is capable of providing basic implementations for some traits via the derive attribute. For more info, please visit here. Let's see, over here we have a tuple struct centimeters, which holds a value of type F64. Now, as you can see, this struct here derives two traits, partial EQ and partial order, meaning the compiler will automatically implement these traits for our type centimeters. Now, partial EQ is for comparing equality and partial order is for ordering. So over here we have inches, and inches is a tuple struct that holds an I32 type. And it derives the debug trait, meaning we can print it out using the debug notation. And as you can see over here, we implement a method 2 centimeters for an instance of the inches type. So when we call this method on an instance of inches, then we will convert it to centimeters, right? So we here dereference self, meaning the instance of inches, and then we the structure over here, the inches, basically the value that the tuple struct inches holds. So this variable then will hold the value of the instance provided here. Okay. And then, as you can see, we are multiplying inches by 2.54 to convert it to centimeters. And we are wrapping that and we are returning that as an instance of centimeters, as you can see. So, add some attributes to make the code work. Don't modify other code. So as you can see over here, we are instantiating the seconds struct. So then we are printing it out using debug notation. So we have to derive over here the debug trait. Then we are here comparing for equality. So we have to derive the partial EQ trait. And over here we are checking if 1 second is bigger than 1 second, meaning we need to implement the partial OR trait like that. And as you can see, we are here instantiating the inches struct, providing it a value of 12, right? This I32 type. And then we print it out, and let's check. Debug is implemented, so we can print it using debug notation. And over here we are instantiating the centimeter struct. As you can see, centimeters takes a value of F64. And over here we are comparing, as you can see over here, this foot instance holding an instance of inches with 12. So in the US, 12 inches equal 1 foot. And then we call the 2 centimeters method on it, meaning this will then return an instance of centimeters, right? So we are taking here inches 12, and that means 12 over here will get destructured, right? Here we have, here self would be inches 12, and we take it as a reference like that. So we destructure it like that using the let keyword, the reference, because we want to take the value and not a reference. And then 12 will be put inside the inches variable. Then we are multiplying by 2.54 and returning an instance of centimeters. And that means we can then compare this over here with the meter, because the meter holds also the same type, namely the custom type centimeters over here, right? So both types would be here of type centimeters. And if this is smaller than this, then it will assign to this variable a string smaller, otherwise bigger. And these are string literals, by the way. And over here we are outputting the result of this compare. Let's see. And as you can see, this is compiling. So we are outputting here 1 second looks like seconds 1. As you can see, we can output this type over here seconds because we have derived the debug trait, meaning we can use debug notation. Then 1 foot equals inches 12. And over here, this 1 foot is smaller than 1 meter. Operator. In Rust, many of the operators can be overloaded via traits. That is, some operators can be used to accomplish different tasks based on their input arguments. This is possible because operators are syntactic sugar for method call. For example, the plus operator in a plus b calls the add method, as in a add b. Over here, this would be a method. This add method is part of the add trait. Hence, the plus operator can be used by any implementer of the add trait. So, implement the function multiply to make the code work. As mentioned above, plus needs t to implement standard ops add trait. That's why we are here importing the ops module from standard library. So let's implement the multiply function. As you can see over here, we are providing 2 U8 integers to the multiply function. Now in the second call over here, we are providing float, means we need a generic type parameter like that. So this function takes 2 arguments, and it will return t, basically the same type of the provided arguments. And then over here, we basically just want to multiply a by b. Now, as you can see over here, we are using the operator for multiplications. And that means we have to ensure that the t over here, the type of the arguments that the multiply function takes, implements the mul trait. Now the mul trait, like the add trait over here, then knows that if both of the types of A and B implement the mul trait, it is possible to multiply these two together. So we can use here a trait bound, meaning the type T over here should implement the standard ops mul trait, because again this is just overloading and syntactic sugar for this call, right? So this actually would translate to this, and we have seen in the add over here that it would be A add B, right? These operators are just overloaded, so it's easier to use. And that's why we have to ensure that A, this argument here of type T, has actually implemented the mul method. And we make sure that this is the case when providing here a trait bound, meaning T must implement the mul trait, meaning then that T has implemented the mul method. Let's see. And we have here to also define that the output will be of type T, because as you can see, the mul trait over here has an associated type of output, so we have to define that. And we will take a look at associated types, but we have here to define that the output should of type T, that the output should be of type T, right? Let's see again. And this is working. Fix the errors, don't modify the code in main. So over here again we are using the ops module from the standard library. Then we have here two structs, foo and bar, and foobar and barfoo. The standard ops add trait is used to specify the functionality of the plus operator. Here we make add bar the trait for addition with a right hand side of type bar. The following block implements the operation foo plus bar should return barfoo. So if we use the plus operator with these two types over here, we should return this type, right? Foo plus bar should return foobar. Now let's see the add trait. Now the add trait over here takes as default parameter RHS, standing for right hand side. If we don't provide anything to right hand side, then it will be self, meaning the type we implement the add trait on. And as you can see, we have an associated type here for the output. And over here, as you can see, add takes self and basically becomes the owner when called on an instance that implements the add trait. And right hand side is of type right hand side, which means by default it would be self. And this looks confusing, I know, but you will get it when we implement that over here. So as you can see, we are implementing from the ops module the add trait. So we can implement from the standard library traits for our custom types. And let's see. Again, when doing something like that, then the compiler will actually do something like that. Right? It will call the add method. Now this over here is the type. Here would be an instance of foo, but just so you get the concept. And as you can see, we have here to define the right hand side, meaning the right hand side over here would be bar, and we are implementing the add trait for foo, right? Because we want the instance to be of type foo, so we implement it for foo. And we want the right hand side to be of type bar. Now if we wanted to add, for example, foo plus foo, then we could omit that, because you have seen that the default is self, right? So the default right hand side would be self, as you can see. So we can omit that, but that means both types must be the same. In this case, foo and foo, right? Because self over here refers to the type we are implement the trait for, right? But in this case, it would be bar, right? Because the right hand side is different from the left hand side. And the output should be of type foobar. So and again, associated functions, we will cover that very soon. So over here, we have to implement the add method, right? Because the add trait over here defines an add method. So we have to implement it. And that means we take self, and this is taking ownership of an instance of foo, right? And right hand side would be of type bar. Again, as you can see, foo would be the instance, then we call the add method upon the instance, and this argument should be of type bar, and then we return foobar. So in main, when we perform this over here, foo plus bar, we will get back foobar, right? So we have implemented the plus operator on our custom types. Now let's do the same for minus sign, but in this case, foo minus bar would be bar foo. So let's see. As you can see, this would be the struct we want to return, bar foo. So minus sign is actually the same, but implementing the sub trait. So we would have foo sub bar, right? This would be the sub method defined in the sub trait. As you can see, we are here implementing the sub trait from the ops module for bar. Now again, we want actually to implement it for foo, because here we call foo sub bar, meaning we would implement it for the foo instance. Because self over here refers to the instance the method is called upon, right? So the sub will be called upon self, meaning we have to implement it for foo. And the right hand side would be bar. Now we want to return bar foo, that's true. And over here, as you can see, the sub method is implemented, but as right hand side, the type should be bar, right? This is the right hand side of the operation. And we are returning bar foo. So when we do this foo minus bar, we will get back bar foo. So we have overloaded this operator. And of course, to do assert EQ here, because this is a custom type, we have to implement the partial EQ trait. So let's do that. And we also have to implement the debug trait. As you can see, this is compiling, meaning when we use our custom types with these operators, they will return a custom type. And we can do that by implementing from the ops module, from the standard library, the appropriate traits for our custom types. Use trait as function parameters. Instead of a concrete type for the item parameter, we specify the impl keyword and the trait name. This parameter accepts any type that implements the specified trait. As you can see, we have here a trait summary. Implement function summary to make the code work. Fix the errors without removing any code line. So over here we have a struct post with 3 fields of type string. And we implement over here the summary trait for the post struct. Meaning we have to implement the defined method in the trait. So we implement it for post like this. As you can see, we are accessing from the instance. Remember, this is a method, so it refers to an instance it is called upon, right? So we access the fields self.title and self.author, right? Then over here we have a struct weibo with 2 fields of type string. Then we implement the summary trait for weibo, and we then have to implement the method from the trait. All right, because again, when we implement a trait for a type, we have to implement its methods. So this over here accesses the username and content field and prints it out. Now here we have an instance of post, and here we have an instance of weibo. So as you can see, we are here calling the summary function with an argument of post and weibo. So we have to implement this summary function below. Let's do that. Now, as an argument, it takes in the first call post and in the second call weibo, right? 2 different types. But now think about it. What do they share in common? Right, they implement the summary trait, right? We have implemented it for post and for weibo. So we can define over here that the argument provided must be a type that implements the summary trait. And we do it like that. And then inside the function body, we want to take this argument. And again, A is an instance of a type that implements the summary trait. So we are taking A and we call upon it the summarize method. Meaning, in the first one, it will be post.summarize. Now post over here is of type post, meaning we go to post, and as you can see, this would be the summarize method. As you can see, self would refer to the instance, in this case post, this instance over here. So then the summarize method will return a string. So let's actually assign this to a variable. This would then hold this string, and we can then output it. Like that. Let's see. And of course, when we are calling the summary method with an instance, then we can't use the instance again. So let's define here that it should take a reference, right? And as you can see, this is compiling. Now what we can do over here, and this would be exactly the same, we can define here a generic type parameter t, and here define that it should implement summary, right? So we define here the type t, and it should be a type that must implement summary, and then we can write it like that. So A should then be a reference of type T, which implements summary trait. Let's see. As you can see, exactly the same thing. Returning types that implement traits. We can also use the impl trait syntax in the return position to return a value of some type that implements a trait. However, you can only use impl trait if you're returning a single type. Use trait objects instead when you really need to return several types. So over here we have two custom types, sheep and cow. And we have one trait animal, which has one method. So over here we are then implementing the animal trait for both of these custom types. And as you can see, when we implement a trait for a concrete type, then we have to implement the given method. So over here we have a function random animal. It takes a random number and then looks if the random number is less than 0.5, it will return a sheep instance. Otherwise, it will return a cow instance. Now over here, the return type of the function would be a type that implements the animal trait, which both of them do. And as you can see in main, we have here our random number. And we call this random number on the random animal function. So let's for now assume that this really is random, okay? So that means that when this is passed over here, it could either be a sheep or a cow to be returned here. But the problem here is that the return type in a function must be of known fixed size at compile time, which in this case, sheep might be bigger than cow, or cow might be bigger than sheep. So the exact size is not known at compile time. So when we do that, this doesn't work. And to make that work, we have to know about trait objects. So let's see. So trait objects using impl trait doesn't work when returning multiple types. Different implementations of a trait probably use different amounts of memory, but sizes of types must be known at compile time. In this case, a trait object can be used. A trait object is essentially a pointer to any type that implements the given trait, where the precise type can only be known at runtime. So Over here, for example, we have a trait animal and two custom types, dog and cat. Then we implement the trait animal for both of these types. And as you can see, we have a function return animal. It takes a string, and if this string is dog, then it returns a dog instance. Now, if it returns cat, then it returns a cat instance. But as you can see, we are here providing a reference to the instance and not the instance itself. Because when we return a reference to a type that implements the animal trait, it means that the size of this type is known at compile time. Because remember, a reference is a pointer, and the size of a pointer is known at compile time, meaning it's of type usize, and usize is 8 bytes on a 64-bit computer. So the size of the return type is known. It's just a pointer-sized type. So the size of the return type is known at compile time. It's of size usize, right? Because we are here returning a pointer, meaning it doesn't matter if dog is bigger than cat or otherwise, it's always the same size, because pointers have a fixed size at compile time. And that is how we would solve this problem. So again, here we have a function which returns a type that implements the animal trait. This could be dog or cat. As the trait object is behind a pointer, the size is known at compile time, which is usize, the size of a pointer. This allows for more flexible code, as the exact return type doesn't have to be known at compile time as long as the size is fixed. So we don't care anymore about the size of dog and cat because they are behind a pointer. And to understand what's going on, you have to know about static and dynamic dispatch. So let's first look at static dispatch. Static dispatch resolves method calls at compile time. The compiler will generate function code for each concrete type that implements the trait. It calls the appropriate function based on concrete types. It's faster and more efficient than dynamic dispatch, but it doesn't provide great flexibility. So we have here the trait animal holding one method, say hi. Then we have dog and cat, and we implement the animal trait for dog and for cat. Now, as you can see, when we create an instance from dog and from cat and call the say hi method on it, because as you can see, every type that implements the animal trait must have this method. And when we then run this program, then the compiler will actually generate methods for each concrete type, in this case dog or cat, because then the say hi method we are calling here on the dog and cat instance is known at compile time. So the compiler then knows when we call the method on the dog or cat instance which method has to be resolved for which type. So let's see dynamic dispatch. In dynamic dispatch, the specific methods to be called is determined at runtime and not at compile time like static dispatch. It works by creating a reference or smart pointer to a trait object using reference_din or box_din. When trait object is created, the compiler will build a vtable for that trait. A vtable is a table that contains a pointer to the implementation of each method in the trait for the specific type of the object that the reference points to. The compiler will do a lookup in a vtable to determine which method should be called for which type that implements the given trait. And this lookup will cause overhead but allows for more flexible code. So exactly because of this lookup, static dispatch is faster than dynamic dispatch. But on the other hand, dynamic dispatch allows for more flexibility. So let's see how that might look like. As you remember, with Box we are able to allocate a type to heap memory, meaning the type will then get allocated. For example, a i32 integer like 7 will get allocated to the heap, and we will then get back a pointer. This is what Box is for, and we have seen examples of that. Now, when we use Box with a trait object, it means that the type that implements the specific trait will get allocated in heap memory. We'll get back a pointer to the location where the type that implements the specific trait was allocated. And we will get back a v pointer, right? This is happening when dynamically dispatching. So the v pointer points to the v table. And in the v table, there are certain fields. Now, there is also a field called methods, and this is where all the methods for the concrete type over here are located. Meaning, at runtime, the compiler will check this v table and see in the methods over here which methods are implemented for the concrete type that was allocated in heap memory. So let's see an example. So we have over here a trait animal, and we have two custom types, cat and dog, and we implement this method defined in the trait for both of our types, right? Because when we implement a trait for a custom type, we have to implement all of its defined methods. So over here, we have seen we have a random animal function, which takes a random number, and based on this conditional, it will either output a cat instance or a dog instance. So then when we call this random animal function with the random number, and for now just assume that this is really a random number, that means the compiler first of all cannot determine the size of the type which gets returned, and this is of type that implements the animal trait, right? Cat and dog both implement the trait, but we can't know the exact size at compile time, meaning we put it behind a pointer, in this case a box, but a reference would also be possible. And that means the size is now known, right? It's the size of a pointer, basically usize, 8 bytes in a 64-bit computer. But we have another problem. Over here, the return value will be a type that implements the animal trait. But at compile time, when we call the noise method over here, the compiler doesn't know which of these types get returned. So the compiler can't know which method he has to call. Is it for the implementation on cat or dog, right? So this is why we use dynamic dispatch, because that means this over here will get decided at runtime. So again, the compiler will then look up in this v table over here using the v pointer, which points to the v table stored in heap memory. And then it will check for the concrete type that got allocated on heap memory the specific methods. So for example, again, this is happening at runtime. We return a cat, then the compiler will see that the type over here, which is concrete, is cat. So it will see in the vtable the methods implemented for the concrete type of cat. I hope this makes sense. So this is why we need dynamic dispatch here. Static dispatch doesn't work, because again, the output of this function is random. So let's see box. Box is a smart pointer that allows to store data on the heap rather than the stack. And you can use box when you have a type whose size can't be known at compile time. It returns a pointer to the data stored on the heap. So what's the difference between a reference and a box? In terms of memory, a box allocates the data on the heap and owns it. It's also responsible for deallocating when the value goes out of scope, and the reference only points to a value that is already in memory, meaning the reference points to something that is already there, while a box allocates, and the reference also doesn't own anything, it just points to something. In terms of lifetimes, a box can be passed across scopes, while a reference has limited lifetime, and we will cover lifetimes very soon. A box can be cloned and a reference cannot, and a box can also be used in pattern matching. So we have left off over here, and I hope by now you know that this over here is not possible. We cannot return a type which implements the animal trait because these could vary in size. And again, over here we return a type that implements the animal trait. Now, if this over here would be really a random number, then we don't know exactly at compile time which type gets returned, meaning we can't use here the noise method, because the compiler can impossibly know at compile time, of course, which method he has to call. Is it this one or is it this one, right? And for that we will use dynamic dispatch. So again, we can put this in a box and using here the din keyword, meaning we want to go with dynamic dispatch here. And that means we have to box these instances. So now the return type over here is known at compile time, meaning we can annotate it. It would be a box which holds a type that implements the animal trait. And this is using dynamic dispatch, meaning we then can call this noise method on this instance here. Because the compiler can check for this noise method at runtime and not at compile time, meaning it is determined which of these will get called at runtime when the program is running. Let's see. And this is working. Trait bound. The impl trait syntax works for straightforward cases, but is actually syntax sugar for a longer form, which is called a trait bound. When working with generics, the type parameters often must use traits as bounds to stipulate what functionality a type implements. So over here we are calling the sum function with two arguments. In this case, two i32 arguments. And as you can see, we could also call this with floats because we have here defined the t generic type parameter. So as you notice, x and y must be of the same type t, and the type will be t, which gets returned. And all we do over here is adding x plus y. Now again, to use this plus operator here, we must define that t over here is a type that implements the add trait. Because remember, this would actually translate to this. So it's critical that x implements the add trait, right? And we also have to define over here the associated type output to be of type t. Let's see. This is compiling. Let's actually call the function and print out the result. So as you can see, the output would be 10. And we can call it with floats, right? So let's see exercise 8, fix the errors. As you can see, we have a pair struct which has two fields holding values of type t, meaning they are generic. And then we have an implementation block for pair, and we define here an associated function. And this is not a method because it doesn't have self as parameter. Now over here we are instantiating a new pair. And remember, self over here, uppercase S, refers to the type of the implementation block, meaning pair. And then we return this instance. So if I write pair here, it would be the same thing. Then over here we have another implementation block for the type pair. And as you can see, we define here that t over here should implement the debug and partial OR. So the type t over here, the type of the two fields, must implement debug and partial OR. Then over here we are defining a method compare display, which takes a reference to an instance of pair. And then checking over here, is the value of the x field bigger than or equal to the value of the y field? If that is the case, then self.x will get printed out using debug notation. That is why we need t to implement the debug trait. Otherwise, we print out the value of the y field. So as you can see over here, we have a custom type unit that holds an i32 integer. Now over here, we are instantiating a pair struct. And as you can see, we are passing here as concrete values for x and y fields the unit type, our custom type. And over here it holds 1 and here 3, right? An i32. The type annotation for that would be, we would have a pair instance, and t over here would be unit, right? Because x and y hold a type of unit. So t over here will be unit. Now remember, we have over here an associated function. So let's actually use that to instantiate a pair. As you can see, this is exactly the same thing as this, but here we are using the new associated function that got implemented on the pair type. So I can delete that. And again, when we call on this instance the compare display method, then we would have an error, because as for now, doesn't implement the debug and partial order traits. So we have to derive them. And by the way, we also need the partial EQ trait. And that's because we are here checking for equality. All right, so we need partial equality. And because we have now derived these traits for this type, it means unit implements debug, partial order, and partial EQ, meaning we can over here compare for equality and ordering, and we can print the field out using debug notation. Let's see. And this is running. So the largest member is Y unit 2. So we have here a pair with an X field of unit 1 and a Y field of unit 2. And then the compare display method will give us back unit 2, right? Because the Y field holds a value that is bigger than the X field. Compare these two, because this is a custom type, is only possible because we have derived these traits. Alright, see you in the next topic. So before doing more exercises on trait objects, I want to cover associated types. Now an associated type allows to specify a type that is associated with the trait. When implementing the trait for a specific type, we have to specify the concrete type. It's basically a type placeholder that the trait methods can use in their signature. And it's similar to generic types, but they are more flexible because they allow a trait to have different associated types for different implementing types. Let's see an example. We have here the myTrait, and this has an associated type called myType. And as you can see, we can then use this associated type over here in the methods we are defining in the trait. So we here, for example, define that the return type should be of type myType. Meaning when we implement this trait over here for a concrete type, like for example myStruct, then we have to define the concrete type. As you can see, when we implement the myTrait for myStruct, we define here that myType should be i32. And as you can see, this method over here will then return an i32 type. And this is defined over here. And we can access the associated type using self, uppercase, double colon, and the name of the associated type. Now again, self here stands for the type we are implementing this trait for. So in this case, myStruct. Alright, let's do some more exercises practicing trait objects. As you can see, we have here a trait bird that has one method. Then we have here two custom types, duck and swan. So let's see, for duck we have an implementation block, and here we define a method. And this method takes a reference to the instance and prints out something. And for swan we also implement a method. Now notice, this has nothing to do with the trait. These are methods that are defined directly on the struct, right? So here we define a method fly, which again takes a reference to the instance and prints out something. Now over here we are implementing the bird trait for duck and swan, meaning we have to implement the method defined by the trait. So as you can see, this quack method we have to implement for both types. Then over here we want to instantiate a duck. So we then can call on this duck instance the swim method. So this will then get executed. Then over here we call the hatch a bird function with an argument of 2. And over here we call the hatch a bird function again with an argument of 1. So as you can see, when we provide 2, we want over here a duck. When we provide 1, we want over here a swan. And I see that because of the output when calling the quack method. So let's implement this function. We have seen that the function takes as an argument an integer. So let's call the argument species and let's define it as U8. Now I will keep the return type open. We will see that then. So let's see, when we get 1, let's actually match the species argument. When we get back 1, we want to return a swan. Right? If we get here for the argument a2, we want to return a duck instance. And because we have to handle all the cases, I will just panic in case anything else has been passed. So over here, what would be the return type? Now think about it. When calling this function over here, we have to provide the return type. Now, again, the return type has to be of known fixed size at compile time. Now, over here, we don't know what will get actually returned at compile time, right? Especially if this argument over here would be something that is generated at runtime, meaning we don't know the exact size because this swan struct could be larger in size than the duck struct or otherwise. So we have actually seen the solution. We need to box the return type, and we over here define that it should be dynamically dispatched. And that means we have to box these concrete values here. And now we are good to go, because also another problem would be that in a match, every return type has to be of the same type. Now again, over here, the function could sometimes return a swan or sometimes a duck, right? Depending on the argument. And when we do it like that, we actually return a type of box, right? So they have all the same return type. Now again, because we are here using dynamic dispatch, we have to put it behind a kind of pointer. And that means over here, we will get a box holding a trait object. And the trait object in this case is bird. So that means, and we have seen that the compiler will then allocate the concrete type, for example, over here, duck, in the heap memory and will create a V table with all the methods. Because when we call over here the quack method on bird, then at this exact point dynamic dispatch happens. Because it is not known at compile time which concrete type got returned here, this will be determined at runtime. So at runtime the compiler will check the vtable and see the right and will execute the right method call, right? In this case it would be for duck. So the compiler will look this method up in the vtable for the duck type, which has been allocated in heap memory. And we got, and notice something over here. When we return a trait object, the trait object actually only implements the methods from the trait, in this case bird, right? So we then can't call, because we have here a trait object, we can't call a method directly defined on the type. So for example, this swim method is not in the vtable that the compiler creates. I hope you see that, because again we are returning a trait object, meaning in the vtable are only the methods from the trait. So over here, because we have created an instance on the concrete type, we can call the swim method. But over here, because we have a trait object, we can only call methods from the trait. Let's see. And as you can see, this is compiling. Array with trait objects. Again, we have the bird trait with the same method. Then we have duck and swan. And as you can see, these are methods that are implemented directly on the concrete type. Then over here, again, implementing the bird trait for duck and swan. We have seen that. Fill in the blank to make the code work. So over here, we want to have an array, because we are here iterating over this bird's variable, meaning we want to iterate over an array. Now let's first annotate. We want over here an array of birds, right? So we want a type that implements the bird trait, meaning in this case duck and swan. And this time I will use a reference instead of a box. So we define over here that we want an array holding a type that implements the bird trait and is dynamically dispatched. All right. And again, because using dynamic dispatch requires that we put it behind some kind of pointer, either box or a reference. Now in this array, let's say we want to have two elements, one duck and one swan. So let's provide here the instances. And again, we have to put that behind a pointer so the size is known. So the size is known at compile time, because remember, the size of the elements in an array must be known at compile time. In this case, it would be usize, the size of a pointer. Now then we want over here to iterate over these elements here. And then, as you can see, for each element we are calling on it the quack method. Now again, because this over here is happening at runtime, the quack method will be determined at runtime which one to run here, for duck or for swan. All right, let's see. And this is compiling. Now over and here we have the same thing, bird.fly. The method we have directly implemented on the type isn't available, because in a trait object over here, only the methods from the actual trait bird are in the vtable. Other methods won't get into the vtable, and so the compiler cannot look it up at runtime. Referenced in and boxed in. So we have here a trait draw, which has one method, and we implement the draw trait for U8 and F64. As you can see, we can implement our own custom traits for types in the standard library. And all this does over here is it will take a reference of the instance and it will output the value. Now in the newer version of Rust, we don't have to dereference self here. This is happening automatically. Like that. And for F64, the same thing. Now, as you can see, we have here an F64 and an U8. Basically the types that implement this draw trait. Then over here we are calling the function draw with box. And as you can see, this function over here expects a trait object of the draw trait. And this trait object should be boxed. Alright, and then it is calling the draw method. Again, the compiler will then look in the vtable and will execute the appropriate method at runtime. So let's pass the argument for the draw with box function, and in this case we want to draw x, so let's pass it x. And of course this has to be boxed, right? Like this. Now over here we want to draw y, and this time we are passing a reference, meaning we over here expect a reference to a trait object that implements the draw trait. Alright? And then we are calling the draw method again, this time on y. Let's see. And this is compiling. Let's see exercise 4. We have a trait foo, which has one method. Then we implement foo for U8 and string types. And as you can see, we can implement our own traits on types that are defined in the standard library. So in this case, U8 and string. Then over here in main, we have a variable x holding a U8 and y holding a string. Basically the types we are implementing foo for, right? And let's see now the function call static dispatch. So we pass here x, the U8 type, and this should be statically dispatched. So let's implement this function. Implement below with generics. So we need here a generic type parameter, and we define here a trait bound, meaning we want t to implement the foo trait, right? Because we want the argument to be of type t. So it's important that we define here the trait bound, because we call this function only with arguments that implement the foo trait. And we are defining that in order to be able to call the method on it. Basically this method defined here, right? Because then we can pass types of U8 and string to this function, and it can call the method because the foo trait is implemented for this type. Any other type that doesn't implement the foo trait won't be allowed to be passed to this function. So this is static dispatch, because the compiler at compile time will actually expand this code and create a function for the concrete types. So in this case, we are passing U8 to this function. So the compiler will create a function like this. Right? And then we'll call it. And this is happening at compile time, meaning the compiler will fill in the concrete types over here. And then, of course, the compiler will know when we do a method call, which method over here it should call, right? And static dispatch is usually a lot faster than dynamic dispatch, because you don't have to do a lookup. It's everything in the binary itself. But when you have to do a lookup, you have to follow a pointer to heap memory and then get the data from this memory location, which is more expensive. So let's see dynamic dispatch in this case. And we use dynamic dispatch because sometimes it's just not possible to use static dispatch, right? When the size of the returned type cannot be known at compile time, then we use dynamic dispatch. And let's see how that looks like. So over here, we are passing a reference to y. So we are passing here a reference to a string. Now, as an argument over here, we want a reference, right? That's what we are passing to a trait object, implementing the foo trait, all right? And again, because this is dynamic dispatch, so this happens at runtime, it must be behind a pointer. So the size is known at compile time, because a pointer is always of size usize. We have covered that. And then we call the method on the argument, right? The difference is that over here, this will then be determined at runtime, which method over here to be called, right? Because the compiler will then do a lookup in the v table at runtime and then determine for which type the method should be called. Let's see. This is compiling. Object safe. You can only make object safe traits into trait objects. A trait is object safe if all the methods defined in the trait have the following properties. The return type isn't self and there are no generic type parameters. So let's see exercise 5. Use at least 2 approaches to make it work. Don't add, remove any code line. So I think we will go first with static dispatch because it's easier. So I will remove this box here. And let's see, we have a trait here defining one method. Now this defines that it takes a reference to a self, meaning a reference to an instance of my trait, and it returns self, where self over here refers to the type for which the my trait is implemented. So in this case, for example, over here, my trait is implemented for U32, meaning we implement this method over here, and self over here would refer to U32, right? We can write it either way. And u32 and string implement myTrade. Alright, so they both implement the f method. Then over here we have a function that takes a trade object. Now in this case we want to use static dispatch, so we define here a generic type, right? Because we are calling it with u32 and a string. Now we want to ensure that T, this type, implements myTrade. So we can be sure that it implements this f method. So this is called trade bound, and this makes sure that T implements myTrade. So we then can call the f method on the provided argument here, which is of type T. And that's basically it. We have implemented the static dispatch for this function over here. And what then will happen is when we call this function, the Rust compiler will take this generic function here and it will provide it with concrete types. And it will provide it with concrete types. So in this case, u32, right? We are passing it u32. And we forgot to define the return type. So the return type over here would be the return type of the f method. Now in this case, it would be the type, right? So if we are calling it, so if we are calling the f method on an u32, then the return type will be u32. If we call it on a string, then the return type will be string. So again, we pass here T, right? Because the type we are passing, for example, u32, will be the return type of this function, u32. And that in case means that the return type of this function over here will be u32, right? And then the same thing happens for a string. So the compiler will actually put into these generic type parameters concrete types. And that means when we are using static dispatch, these method calls here are known at compile time. So the compiler knows if you're passing a u32 type, then it will call the f method from the u32 implementation of myTrade, right? And in case of string, then the compiler will know that the f method can be found in the myTrade implementation of string, right? So everything here is known at compile time, and also the size is fixed. And this is working. Now we want here to now use dynamic dispatch. So we solve it in two approaches. So before we can even use this trade object over here, we have to make the trade itself object safe. And we do that when the return type isn't self and there are no generic type parameters. So we cannot define here self. We have to provide it concrete types. Now in this case, we want the f method to return a trade object, meaning we return a pointer that points to the type that implements myTrade. All right. And over here, because we are taking here this function signature and implement it for each type we implement the myTrade for. So as you can see, the return type must implement the myTrade and it has to be boxed. So we have to box this over here. Turn over here a U32, right? Which implements the my trait. And over here, a string. Which also implements my trait. So as you can see, we got rid of self because again, at compile time, the return type size has to be known. That's why we are putting it behind a box. Now, again, the return type of this function would be the return type of the method calls. In this case, it would be a boxed trait object, right? Let's see if this is compiling. And this is also compiling. Now, I hope you see the difference here. When we pass here a trait object, basically a type, in this case U32, that implements the myTrait trait, then this method call will be determined at runtime. And that's why we have to put these behind pointers, so the size remains fixed and known at compile time. And again, use whenever possible static dispatch because it's faster and I guess easier to write, but dynamic dispatch has its advantages and you can use it for more flexibility in your code. Alright, see you in the next topic. So we have reached the topic of collection types, and string is also a collection type, meaning we are just repeating because we have covered strings, but I think these exercises are good for some repetitions. So string is a UTF-8 encoded growable string. It is the most common string type we used in daily development. It also has ownership over the string contents. So let's see, fill in the blanks and fix errors, don't use toString, don't add, remove any code line. So as you can see over here, we want a string type because we are here modifying the string, meaning it has to be growable. So let's allocate this data over here on the heap. So we have now a string type. Now let's see the pushStir method. As you can see, this pushStir method is implemented on the string type, and it takes as a type for its argument a string literal. As you can see, we are calling it on a string and providing it an argument of a string literal. So we have to delete that because this would actually be a string, right? We want here a string literal, like that. And push is for pushing single characters. So we want to push here an exclamation mark. So S will then here match with this string literal. And as you can see, we are calling the move ownership function here, meaning this function will then take ownership of S, and that's not what we want because we are using here S again. So what we can do is just clone it. So the data passed to move ownership over here is actually cloned, right? It is copied on the heap memory. And that means we can still use S because S remains the owner of this data. All right. Then a string is stored as a vector of bytes but guaranteed to always be a valid UTF-8 sequence. String is heap allocated, growable, and not null terminated. A string slice is a slice, basically a slice to U8 integers, because as you can see, this string type is a vector of U8 integers. That always points to a valid UTF-8 sequence and can be used to view into a string, just like a slice to T is a view into vector T. And we'll cover vectors after this topic. So fill in the blanks. We have here a string, and we want to take a string slice from this string. Now the easiest method would be just to take a reference to S, which means we take a reference to a string type. And this can then be inferred by the compiler to a string slice. And the second way would be to call the stir method on it. This will essentially do exactly the same thing. It will take this string S and will convert it to a string slice. Now over here we also want a string slice, but we want to provide a specific offset. We just want this data over here, and that means we take a reference to S and provide it here an offset from 0. We can omit the 0 on here until index 0, 1, 2, 3, 4 until index 4. Now we would provide here 5 because 5 is excluded, meaning we go from index 0 to 4. And over here, as you can see, we want to modify the string, holding then hello world, because we are pushing to it this exclamation mark. As you can see, we want it hello world and with an exclamation mark. So what we can do is taking S over here as mutable reference. So this would then hold a mutable reference to a string. Let's see. And this is compiling. Now notice over here we could also take ownership of S, meaning slice3 will hold a string because we are not using S after this point. So slice3 can be the owner of S, but in this case we have to make the variable mutable. And this is also working. Question: how many heap allocations are happening here? So we have here a string, and when we create a string type, then the data that is provided is allocated in heap memory. So this would be the first allocation. Then over here we are taking from this string over here a reference, meaning a string slice. And remember, a string slice is just a view into some data. So we are just going to this location and checking what's in there. So no allocation is happening. And over here we are taking this string slice and convert it to a string, meaning a heap allocation is happening over here, right? Because we are taking this string slice holding this, and then we allocate this into the heap once more because we are calling this toString method. Let's see, indexing. So we have a string here and we want to index into the first element. So slice1 should then hold age. So we want a string slice. So we take a reference to S and provided the offset from 0 to 1, where 1 is excluded, meaning we just take the first character. And that is because age only takes 1 byte in UTF-8 format. So ASCII characters in strings usually take 1 byte, while these Unicode characters over here take 3 bytes. So when we take a string slice here, we want to access this character. Now for that we have to provide the right offset. So we go from 0, 1, 2, 3, 4, 5, 6, 7, starting at index 7, and as you can see, these Unicode characters hold 3 bytes, meaning we must provide here an offset of 10. 10 is excluded, meaning we go from 7, 8, 9, 3 bytes. Iterate through all chars in S. So to iterate over characters in a string type, we use the chars method. But that will actually just return the char we are iterating over. But as you can see, we want here as return type a tuple which holds the index and the actual character. So we can use here the enumerate method. And enumerate will return a tuple with the index and the specific character. So in the first iteration we would have 0 and age, right? The index and the character. So here we are checking if the index over here is 7, then the variable c should hold this character, right? Let's see. And this is compiling. Now there is a crate called UTF-8 slice. You can import it into your project, and this then allows you to slice into a string, not using bytes as offsets, but just indexing into the individual characters. So over here we provide an offset from 4 to 5, meaning we want the character at index 4. So we don't have to worry about the byte size of this symbol. Then fill in the blanks. We have here a string. Now we have seen that a string is actually a vector holding U8 integers. And as you can see, we have here some bytes in a vector. So this vector holds U8 integers, right? And that means these are bytes that can be converted to ASCII characters. So in this case, these over here would translate to hello. Alright? If you look up this code over here in the ASCII table, then we will find that this is represented for the character age. And this ELLO. So we want to turn a bytes vector like this into a string. So we want a string here. So let's see this method here. So in the documentation you can see that the string type implements a method from UTF-8. And this just takes a vector of bytes, and then we can call this associated function on the string type and provide it as an argument a vector of bytes. And this will then convert it to a string. So we can try it out. So first of all, we want to actually mutate the string here to hold the same data as this vector holds, namely hello. So we can do that by using push stir. And we push hello, meaning this string then holds hello. And then we can take this string type and call from UTF-8 method, providing it this vector. And this should then convert this vector of bytes into an actual string, meaning S and S1 will then hold the same value, namely a string hello. And of course this actually this returns a result, so we have to unwrap it. And as you can see, this is compiling. So in fact, a string is just a vector of bytes, right? And we'll cover vectors very soon, and you will then see how this is actually stored in memory. So a string is made up of three components: a pointer to some bytes, a length, and a capacity. The pointer points to an internal buffer string uses to store its data. The length is the number of bytes currently stored in the buffer, always stored on the heap. And the capacity is the size of the buffer in bytes. As such, the length will always be less than or equal to the capacity. We have seen that the string type is a three-word object holding a pointer to the actual data stored in heap memory, the length, which shows the length of the string, in this case 5, and the capacity. And the capacity, as you can see here, is the total amount of memory received from the allocator. So when we allocate a new string type on the heap, the allocator will find an empty spot and then will return a pointer to that location. So, number 6, if a string has enough capacity, adding elements to it will not reallocate. So when we run this program over here, then we see the capacity of string s. Now over here we are initializing an empty string, meaning we have an empty string, so nothing gets allocated to heap memory. We still have a string object, but with a length of 0 and a capacity of 0. Then we print it out, as you can see, 0. Over here we are iterating 2 times, modifying this string. So in the first iteration, s will then hold hello. So it would have a length of 5, but when we print out the capacity, it will show 8. So we have a string object that points to this data with a length of 5 and a capacity of 8. Now this is the default behavior when we don't specify a capacity ourselves. So when the length exceeds the capacity, then Rust has to reallocate the data, meaning it has to find a new spot in heap memory that is big enough to hold the data, and then will return a pointer to the new location. So in this case, because we have modified the string, the length 5 exceeds the capacity 0. So it has to reallocate. Because remember, in heap memory, the data is allocated as contiguous block of bytes. Alright? And the default behavior is that the capacity will always double. So it starts from 1, then 2, 4, 8, 16, and so on. And that's the reason we have here a capacity of 8, even though we only need 5, right? This is a string of length 5. But because of the default behavior of the allocator, we will get back a capacity of 8. And then in the second iteration, we again push hello. Right? So we would have a length of 10. But as you can see, the capacity doubles. So 10 exceeds the length of 8, meaning the allocator will then find a new spot in heap memory to allocate this string over here of length 10, and it will then reserve 16 bytes of memory in heap memory. and so on. If we then exceed 16 bytes, then it will allocate to a location which holds 32, right? It always doubles. And this is when you let Rust allocate. So this is the default behavior. But as you can see, this might be expensive. So if you start with a capacity of 0 and then you modify the string multiple times, it means Rust has to reallocate your data. And that means it could potentially be expensive when you mutate this over here multiple times and a lot of reallocations are happening. So there is a function called with capacity. And then we can define over here that we want an empty string, meaning the string length is 0, but we want a capacity of 25, meaning S is allocated in heap memory and there is enough space reserved for this data to hold 25 elements, right? So when we do that again, then as you can see, no reallocation has happened. We have only allocated the string one time in heap memory with a capacity of 25. Now, because the length doesn't exceed the capacity in any of these modifications of the string, it means that there is no need to reallocate the data, right? So when we print out the string S over here in the end, then as you can see, this is the string that S holds in the end, hello, hello. So we have here 10 elements, meaning there is no need for reallocation because a capacity of 25 can hold the string of this size, and this can make your program a lot faster. So let's see vectors. A vector is like an array but dynamically sized, meaning they can grow and shrink. It's allocated on the heap as contiguous block of memory. All elements in a vector have to have the same type. And there is a special macro vec which you can use to initialize a new vector. So all this time we've been dealing with an imposter. So in actuality, the string type is just a vector of UTF-8 bytes that gets allocated in heap memory. So as you can see, when we have the S1 variable over here, then again, S1 won't hold the actual data, but a pointer to the data allocated in heap memory alongside a length and a capacity, meaning S1 is a 3-word object of size 24 bytes. Now, as you can see, this would be a vector allocated in heap memory that holds the UTF-8 bytes over here. Of course, in memory, this would be in binary, but as you can see, this then holds the character code for this character inside the string. So let's do some exercises. Vectors are resizable arrays. Like slices, their size is not known at compile time, but they can grow or shrink at any time. So over here we have a normal array holding 3 U8 elements. Now we can convert this array to a vector using the from associated function and then passing it the array, meaning V will then hold a vector of U8 elements. And here you can see the difference between an array and a vector. We don't provide here the length of the vector because the vector can actually grow or shrink, meaning it's dynamic in its size. Now the isVec function basically just checks if the provided argument is a vector. Then, as you can see, we are shadowing v, and we are here initializing it with a vector of these elements. So as you can see, you can use the vec macro to quickly create a new vector like that. So this will then hold a vector of u8 elements. And by the way, you can either use square brackets or you can use parentheses. It's both exactly the same. Now, as you can see, here we are initializing v, or basically shadowing it, and then we are passing it to isVec, meaning ownership would be transferred. But we are using v here again, so let's clone this. And over here, as you can see, we are initializing v1 with the vec macro. Now we are passing to the vec macro the array. Now the vec macro over here won't convert it directly to a vector like this from associated function did. Instead, we would here have a vector holding this array. All right. I hope you can see the difference. Here we have a vector of u8 elements. Over here we have a vector holding an array of 3 u8 elements. So when we compare over here v and v1, they won't actually be the same, right? And again, let's do clone here, just so we can then reuse v1. Now what we can do over here to fix that is using the vec new, like that. And vec new basically will then create a new empty vector, meaning it would be an object with length of 0 and capacity of 0. Now over here we want to iterate over the elements in v. Let's take a reference here because we are using v again and we don't want this for loop to take ownership. Now all we want to do is pushing all the elements from v into v1. And because we are here iterating over references of elements, we have to dereference it. And by the way, we will take a look at that in much greater detail. So what we also have to do is making this v1 variable mutable, because when pushing to it, it has to be mutable. All right, let's see. And this is compiling. So in the end, v1 will hold a vector of u8 elements, meaning v and v1 are exactly the same. But remember, when you have an array, use the from associated function and not the vec macro, because it won't convert it directly to a vector. Instead, it will create a vector holding an array. A vec can be extended with extend method. So over here we have a vector. Let's say these are i32 values. And as you can see, we can pop, meaning removing the last element. So over here, the vector will then hold 1 and 2 because the last element got popped. Then we are pushing to it 3. Meaning we have a vector holding 1, 2, 3. Now over here again we are initializing an empty vector. Now as you can see, we want v1 and v2 to be exactly the same. So what we can do is using the extend method and providing it the v1 vector, meaning the elements and we have to pass here a reference, meaning the elements then from v1 will be put into v2. So again, v2 will then be a vector of i32 elements, and they hold exactly the same data, right? It's basically copying the contents of a vector into another vector. Turn x into vec, fill in the blanks. So over here we have an array, and this array holds i32 types, and the size of the array would be 3. Then, as we've seen, we can use the from associated function. So we create a vector from this array, meaning v1 will then hold a vector of i32 types. Or what we also could do is calling the into method, and if a type implements from, then it will implement into, and we will take a look at that. So we then take this array over here and convert it into a vector of i32 values, right? So that means v1 and v2 will be exactly the same. Now converting a string into a vector. So the from trait over here is actually implemented for the vector type. So over here we have a string, and remember, basically a string is a vector of u8 elements. And then again we can call here into, right? Converting s into a vector of u8 elements. And then over here we have again a string, and we call the method into bytes, meaning v2 holds a vector of UTF-8 bytes, represented as u8. And this is actually exactly the same. So meaning v1 and v2 will be identical. Then over here we have a string literal, and we want to create a vector from this variable, meaning we again use the from associated function and provide it as an argument over here, meaning v3 will then hold a vector of u8 types, right? So v2 over here and v3 are identical. Iterators can be collected into vectors. So when we have here an array of 10 elements of value 0 and we put it into an iterator, we can then collect it into a vector. All right, and we will see these methods over here, into iter and collect, in much greater detail. Meaning v4 will then hold a vector of 10 times 0. Like that. All right, let's see. And this is compiling. Fix the error and implement the code. So let's see, over here we have an array, and we convert this array into a vector using the from associated function we have seen. So this will then hold a vector of i32 types. All right. Now then we are iterating here 5 times and just print out each element at the specific index. Here we have to implement some code, and actually v in the end should hold a vector with these elements. So as you can see, we are starting with a vector holding 1, 2, 3, and we end with a vector 2, 3, 4, 5, 6. Now, what we want to achieve here is we are adding 1 to each element. Then we would have 2, 3, and 4. Now, if we exceed the boundary over here, then we want actually to add the new element over here. Now, let's see first in the for loop here, this would actually panic because we are trying to access indexes that are out of bounds. So over here we are iterating from 0 to 4, right? 5 excluded, but we have only 3 elements, meaning indexes 0 to 2. Now we can here use the get method, and we have seen this get method before, and this is generally safer because it will return an option. In this case, option I32, because we are dealing with I32 types here. And what we then can do over here, we want to actually manipulate this vector. So let's first access the elements. And as you can see, again, I use the get method because we want to actually see if the index is out of bounds or not. So in case it's not out of bounds, we would return a sum, right? The get method will return a sum and the actual value at that specific index. So if we found an element at the specific index over here, then we want to access the element and just add to it 1, right? So we are then taking the element over here. Let's see, for example, in the first iteration, I will be 0. Then we pass 0 to this get method, meaning we will get back some 1, right? So we'll get back some 1, meaning E over here will then hold a value of 1. Then we access this array at index 0, right? And what we want then to do is taking 1, E over here, and add to it 1, meaning then the first element in this vector has been modified to then hold 2. Now in the second iteration, it would be exactly the same thing. So I would be 1. We get over here the element at index 1, and E will then hold 2. And then over here, V at index 1 should then hold 2 plus 1, right? And we assign it, meaning in the modified vector, the second element will then hold 3. Now we do that again, and after we are out of boundaries, meaning we return a none here, and then we want to push to the vector the index plus 2, right? So for example, in the third iteration, I would be 3, right? This would be out of bounds. There is no index 3 here. So we get back a none. And then over here, we push to V the index, in this case 3, plus 2, meaning we then get back 5, right? And let's see if this is actually working. Alright, and let's remove this type annotation because this would be of type usize because of the get method. Now, as you can see, when we print out here the output of the get method, we would get some 1, some 2, and some 3, and then 2 times none, because at iteration 3 and 4, we would get back none because there is no element in this index. And we are succeeding here because, again, we have 3 times sum here, and when we have a sum, we just add 1 to the value, meaning we then have 2, 3, and 4. And then we will get back 2 times none, meaning we take the index and increment it by 2, pushing it to the vector. So we get 5 and 6. Slicing. A vec can be mutable. On the other hand, slices are read-only objects. To get a slice, use reference. In Rust, it's more common to pass slices as arguments rather than vectors when you just want to provide read access. The same goes for string and string slices. So over here we have a vector, let's say I32. Then we are taking a slice from V over here, meaning this would then be a slice of I32 elements, right? And this would be the offset, meaning we would take from the first element to the last element. Out of bounds will cause a panic. You must use V length here. So as you can see, again, we are taking a string slice, but we are here out of bounds, right? Because this would iterate from 0 to 3, 4 excluded, and we have here only 0, 1, 2 indexes. So what we can do is using v.length, meaning we just iterate, meaning we provide an offset from 0, the first element, to v length, where the length here is excluded, meaning v length minus 1. All right. Slices are read-only. Node slice and reference to vec are different. So as you can see, we take here a mutable reference to a vector, and then we can push to this vector over here the value 4. Now we have seen that slices are immutable. They are just a view into some data. So we can't use a slice to mutate the vector, right? So over here we want to have a slice of I32 elements, right? Like that. And we can remove the mute keyword over here because again we can't modify slices. So we have pushed to it 4, meaning when we take the slice we want to take also this last pushed element, right? And this is compiling. Capacity. The capacity of a vector is the amount of space allocated for any future elements that will be added onto the vector. This is not to be confused with the length of a vector, which specifies the number of actual elements within the vector. If a vector's length exceeds its capacity will automatically be increased, but its elements will have to be reallocated. For example, a vector with capacity 10 and length 0 would be an empty vector with space for 10 more elements. Pushing 10 or fewer elements onto the vector will not change its capacity or cause reallocation to occur. However, if the vector's length is increased to 11, it will have to reallocate, which can be slow. For this reason, it is recommended to use the withCapacity function whenever possible to specify how big the vector is expected to get. And this we have already covered with strings, but now let's see with vectors. So over here, as you can see, we are initializing an empty vector, but with a capacity of 10. So this object here would hold length of 0 and capacity of 10, meaning the actual elements inside vector are 0. There are no elements, but in heap memory there were 10 locations allocated for this data, right? The vector contains no items even though it has a capacity for more. So when we call the length method over here, we would get back 0, right? Because vec doesn't hold any values. But it has a capacity of 10 because we have defined that over here. These are all done without reallocating. So we are then pushing 10 times to the vector, right? Now this means vec here holds enough space that this is happening without reallocating the vector, right? So after pushing to the vector would be of length 10 and capacity 10, right? So the length must never exceed the capacity, otherwise a reallocation is happening, as you can see here, but this may make the vector reallocate. So we are pushing another element to the vector, meaning the length will be 11. This would exceed the capacity, meaning then this whole vector will be reallocated in heap memory. So when we have a length of 11, then the capacity will be at least 11, but it can be more, because we have seen that the default behavior when reallocating is that the capacity doubles. Fill in an appropriate value to make the for done without reallocating. So as you can see, we have here a vector we want to initialize with a certain capacity. Then we are pushing 100 times to this vector, meaning the length here will be 100. So what we want to do is we want here to initialize a vector with a capacity of 100, meaning we can push 100 times without this vector to be reallocated in heap memory. Store distinct types in vector. The elements in a vector must be the same type. For example, the code below will cause an error. So we have here integers and a float. This would cause an error because again, all of them have to be of the same type. But we can use enums or trait objects to store distinct types. So over here we again see the IP address enum we have seen before in the examples. Now fill in the blank. We want over here a vector that holds IP addresses, meaning at index 0 we want this variant here, and at index 1 we want this variant. Now we can use the vec macro for that. And then over here I just copy this variant and this over here, right? We would then have over here a vector holding types of IP address. And because this is a custom type, we have to actually implement partial EQ here. So I hope you get the concept. We have here a vector holding types of IP address, right? Then over here we have a trait IP address that defines one method display. And then we have two tuple structs, v4 and v6. We implement the IP address trait for v2 struct and v6 struct, meaning we have to implement the specific method. And all it does, it then basically prints out the value that is stored inside the struct. So fill in the blank. As you can see, we want here a vector holding trait objects. Remember, a trait object is boxed or put behind a reference. So over here we have a vector holding boxes, right? And the box holds a trait object, meaning, again, this is using dynamic dispatch, and we want here a type that implements the IP address trait, right? In this case, v4 and v6 both are types that implement IP address. And as you can see, even though we are holding here different types, we can use it using here trait objects to store it in the same vector. Typo. So, and then we are iterating over the vector, and for each element in here we just call the display method that has to be implemented, because we only have types in here that implement the IP address trait. And this is exactly where dynamic dispatch happens, and we have covered that. Let's take a look at hash maps. So a hash map is a data structure to store key value pairs. It's allocated on the heap as it is dynamically sized, meaning it can grow and shrink. It allows for efficient lookup, insertion and deletion of data. So when talking about time complexity, this means accessing and modifying elements, or entries as they are called in hash maps, would be in the best case at constant time, meaning big O of 1. While in the worst case, if you have a lot of collisions, then it would be still linear time, which is still pretty fast, which means big O of n. Each key is hashed to a unique index in the underlying array. So where vectors stores values by an integer index, hash maps store values by key. It is a hash map implemented with quadratic probing and SIMD lookup. By default, a hash map uses a hashing algorithm selected to provide resistance against hash DOS attacks. So over here we find some information about the used algorithm for the hash maps. But let's dive into the exercises. So the first thing is we actually have to use here a namespace. So we are basically importing from the collections module from the standard library the hash map type. And when using vectors or strings, these are all in the prelude, meaning we don't have to import it, but a hash map you have to basically import. So over here we are initializing an empty hash map. Then we insert some entries, and again a hash map holds entries of keys and values. Now important here is that all the keys must be of the same type and all of the values must be of the same type. So this over here would cause an error. And let's go with integers like that. And we annotate the hash map like this, where key stands for key and V stands for value. So over here we use string literals as keys and I32 integers as values. Then, as you can see, we can access the entries in a hash map by using again the get method, which returns an option. We have seen that before when dealing with vectors. So we provide the get method the name of the key, all right? And then we will get back the appropriate value, in this case 98, because we are accessing the entry sun phase, right? So we would get back here a sum, an option I32, right? This would be the return value, sum 98, and this would be the type, option I32. So we can check if the hash map contains a certain key. So for example, if the hash map contains the key Daniel, this would evaluate to true, meaning the code block here will be executed. And we can also index into a hash map using bracket notation, like that. So again, this would then hold the value of the entry Daniel, it would be 95, right? And this would be an I32. Again, notice the difference between indexing like that or indexing using the get method. We will get back the value here directly, while here we get back an option. So get is generally safer. And then over here we are removing Daniel from the hash map, right? So we can use the remove method and provide it the key of the entry we want to delete. Meaning after deleting Daniel over here, the length of the hash map would be 3, right? And we can also iterate over a hash map. So we provide it here, the variable holding the hash map, and then the return would be a tuple holding the key and the value. And then we just print out the key and the value. Let's see. All right, and we would get back here an option holding a reference to I32. All right. And over here too, we would get back a reference. This is what the get method will actually return. So as you can see, we are printing out the hash map. And this would be the key, for example, Ashley, and this would be the value, as you can see. Now notice that the order here is different from what is over there. And that's because a hash map is unordered. So the order won't be retained, all right? And of course, we have only 3 elements here because we have removed the entry of Daniel. Then over here we have an array holding tuples, which holds a string literal and an integer, right? So we have an array of 3 elements, and each element is of type tuple, and inside the tuple is a string literal and an I32. Then over here we are initializing a new empty hash map. Then we iterate over here through the elements of this teams array. So for each element here, we insert into this empty hash map here the name over here, the string, and the value. All right. Implement team map2 in 2 ways. Tips: one of the approaches is to use collect method. So we can also implement a hash map from an array holding tuples of keys and values by using the hash map from function. So we provided here teams, and this will then directly convert this array holding tuples of keys and value pairs to a hash map. Meaning we then have a hash map holding string slice keys and I32 values. All right. And over here we would have the same thing. And then when we compare teams map 1 and teams map 2, they should be equal. Let's see. This is compiling. Now the second approach would be taking this teams array here, and we want to put it into an iterator. And again, we will cover that. And then we call collect. Now when we call the collect method, it will basically collect the elements in this iterator into the type we have annotated here. Again, this would compile because we have in teams map 2 the same keys and values as we have in teams map 1. And as you can see, we don't need to write a full-blown for loop. We can just use some simple methods. Let's see, number 3, fill in the blanks. So type inference lets us omit an explicit type signature, which would be hash map, string slice, and U8 in this example. So again, we don't have to annotate the types. I do it just to make things more clear, but we can leave it at that. Insert a key only if it doesn't already exist. So here we are accessing player stats, this empty hash map, and we call the entry. Now the entry checks if an entry exists with this specific key. And then we can call over here the OR insert method, meaning if this entry doesn't exist, then we insert this key with this value. Meaning when we then access player stats with a key of health, we should get back 100, right? Because this has been inserted over here. Insert a key using a function that provides a new value only if it doesn't already exist. So again, we are trying to access player stats and look for an entry health. Now in this case, this exists, right? Because we have inserted it at that point. Now we can also use here the method OR insert with. The difference to OR insert is that we don't provide a concrete value, but a function pointer. Meaning this function will then get executed. So this function only returns 42. So that means if the entry health doesn't exist, we insert this key with the value of 42. Now again, health exists, meaning when we access health, we would still get 100, right? Because this only executes if entry isn't found. Ensures a value is in the entry by inserting the default if empty, and returns a mutable reference to the value in the entry. So we are here checking for the entry health, and if it doesn't exist, we insert 50, right? So in this case, health already exists, meaning we would get back a mutable reference to the existing value 100, right? So this would be a mutable reference to 100. And because it is mutable, we can then modify the entry manually. So we can here decrement from health, which holds 100, we decrement 50, meaning the health will then hold 50, right? This health variable holds 50. Let's see. And this would be U8 in this case. And this is compiling. So as you can see, when we call entry, it will give us back a mutable reference to the value. If it already exists, to the existing value. If it doesn't exist, it will here create an entry, because this is what the OR insert method does, and will return a mutable reference to the created value. And then we can modify this mutable reference, right? Requirements of hash map key. Any type that implements the EQ and hash traits can be a key in hash map. This includes bool, int, uint, string, and string slices. Note that F32 and F64 do not implement hash, likely because floating point precision errors would make using them as hash map keys horribly error prone. All collection classes implement EQ and hash if their contained type also respectively implements EQ and hash. For example, a vec holding a type T will implement hash if T implements hash. So if the elements in a collection, for example a vector or a tuple or an array, implement the hash trait, then the collection itself will implement hash. Let's see, fix the errors tips derive is usually a good way to implement some common use traits. As you can see, we have here a struct Viking with two fields of type string. And here we have an associate function for Viking, just creating a new Viking instance from the arguments we provide. And as you can see, use a hash map to store the Viking's health points. So we are creating here a hash map from an array holding tuples of keys and values. Now notice we have here a hash map, and the type of the keys would be the custom type Viking, all right? And the value would be I32. Use derived implementation to print the status of the Vikings. So here we are taking this created hash map as a reference, and we would get back a tuple holding the key and the value, and then we just print out the key and the value here. So we have seen that in order a type can be used as a key in a hash map, it has to implement EQ and hash. So let's implement that. Let's also use the partial EQ over here and debug, so we can print out the key over here in debug notation. Let's see. And of course we have to implement the hash trait. And as you can see, it will print out each element in the hash map we have created. So we have now a hash map using as key our custom type Viking. As you can see, this would be the key and this would be the value of the hash map. Capacity. Like vectors, hash maps are growable, but hash maps can also shrink themselves when they have excess space. You can create a hash map with a certain capacity using hash map with capacity, or use hash map new to get a hash map with a default initial capacity. This is recommended. So like we did with strings and vectors, we can define when initializing an empty hash map the capacity, right? Ensuring that when we know we will push a lot of entries, that there are no reallocations, because remember, reallocations are slower. So then we are here inserting 2 entries. And as you can see, this would be an entry of key I32 and value I32. So the key and the value can be of the same type. And over here we insert again another entry. Indeed, the capacity of hash map is not 100, so we can't compare the equality here. So even though we have here defined that the capacity should be 100, it could actually be more than 100, and this is just in case there are collisions, there are some internal stuff going on. So the Rust compiler will actually allocate more capacity than 100 we defined here. Shrinks the capacity of the map with a lower limit. So when we call map over here, our hash map holding 2 entries, and then we can shrink the capacity to 50, right? So again, the capacity won't probably be exactly 50 then, but around 50. So we can shrink the hash map, and shrinks the capacity of the map as much as possible. So because over here we have only a hash map of 2 entries, 50 spaces in heap memory would actually be more than we need. So we can use the shrink to fit method so that the capacity will shrink around the amount of elements it actually holds. Again, it won't probably be 2 exactly, but around this number. Ownership. For types that implement the copy trait like I32, the values are copied into hash map. For owned values like string, the values will be moved and hash map will be the owner of those values. Fix the errors with least changes, don't remove any code line. So over here we have initialized a variable with a type of I32 and an empty hash map, right? Then we insert here an entry into M1 and using the same exact value for the key and the value, meaning we have here a hash map with keys of type I32 and values of type I32. Over here we have a string and we initialize here an empty hash map. Then over here we are inserting a new entry using v2, the string here, as the key and v1 over here as value. So we would have here a hash map using of keys of type string and value of type I32. And because this is an owned type, meaning it doesn't implement copy, this will then actually be moved into the hash map. So we can't use v2 here. But what we could do to fix that is we could use a string slice of this string, right? We just provide a reference, meaning then the hash map will have type for the keys of string slices, right? And that means we can then again use v2. And again, because v1 is of type i32, it means it implements the copy trait, meaning even if we pass it as a key in the hash map or as a value, it is still usable. But when you are dealing with types that don't implement copy, the ownership will get moved, meaning hashmap will then be the owner of the type. Alright, and there are some third-party hash libs, but I won't cover that in this beginner's course. So, see you in the next topic. Let's now look at type coercion, and we have already seen the as keyword, and this is mostly used for converting integers. So type conversion, also called typecasting, is coercing a primitive type that can be performed by as keyword. As conversions can be chained, and when casting to an unsigned type t, for example, then t max plus 1 is added or subtracted until the value fits into the new type. And using unsafe methods can lead to undefined behavior. So let's see an example. As you can see, we have here the largest unsigned 8-bit integer, 255. And this would be the binary representation. This means that U8, right, this data type for unsigned 8-bit integers, max, meaning 255, plus 1 will be 256. So for example, if we typecast 1000 as U8, then let's see what the compiler will do. It will subtract 256, this value over here, from 1000. And then it will check 744 is still bigger than the largest value it can represent, meaning it will do the same thing. Subtracting 256 will leave us with 488, still bigger than this value. So again, the same thing, it will subtract 256 and this will leave us with 232, meaning this will then be the returned value when we cast 1000 as U8. Because remember, an 8-bit unsigned integer can't represent 1000, it's out of bounds. Now, when we typecast -1 as U8, then remember, an unsigned integer cannot represent negative numbers, meaning what it will then do, it will basically rotate. So 0 would be the smallest possible number an 8-bit unsigned integer can represent, and then -1 will just basically rotate. It will go back to the biggest one, meaning this typecasting over here will result in 255. So convert by as. Rust provides no implicit type conversion coercion between primitive types, but explicit type conversions can be performed using the as keyword. Fix the errors and fill in the blank. Don't remove any code. So over here we have an F32 float, right? Then we typecast this float into an U8, meaning over here the fractional part will get removed. So the value would be 97. And of course this will then hold a U8. Now we want to typecast this decimal into a char. Now this is not possible directly, but we have seen that we can chain as statements. So we can convert this first to an U8, meaning we will get 97 like we did here, and then typecast it to a character. So C1 will then hold a character. And by the way, 97 would be the ASCII code for A. And over here, as you can see, we can typecast this integer holding an U8 type as char directly. So C2 would also hold a char. Now, as you can see, we are here comparing the integer holding 97 with this typecasting. Now, this typecasting over here converts the B character to its U8 representation. Now, B would be represented as 98. So what we can do over here is adding 1 to 97, because remember 97 would be A. Meaning when we add 1 to it, we will get back B, right? So both of them will hold 98. By default, overflow will cause compile errors, but we can add a global annotation to suppress these errors. So, as you can see, the largest possible number U8 can represent would be 255, meaning this would cause an error. Because again, 1000 is larger than the largest possible number a U8 can represent, meaning we have here an overflow error. Now we can actually allow overflowing by using this attribute. So this then won't complain, right? And then when we print out V, as you can see, we would get back 232, because we have seen over here that this would be the result when the compiler performs this operation. So we allow here overflowing literals, right? If we comment this out, then the compiler will complain, because this is actually not possible. When casting any value to an unsigned type T, Tmax plus 1 is added or subtracted until the value fits into the new type. That's what we have seen. So in this case,